Thanks very much, Paul. It's a real honor to be here, to be invited to give a presentation here at the Nelson Institute on Earth Day. China, I wish you had been a little less eloquent because you're going to be a very tough act to follow. But I'll give it a shot anyway, and I look forward to the conversation with Earl afterwards. Where are we going to go today? I thought I'd like to start by spending a little time talking about this Anthropocene thing. What is it? What is this new epoch? What does it look like? How is it different from the past? Then talk a little bit about planetary boundaries, because that's a consequence of being in this new epoch. It's essentially the boundary conditions for how this new epoch works. And talk a little bit about implications for sustainability. How can we actually flourish? Not just be sustainable, but can we flourish in this new epoch? Yes, it is possible, but we've got to sort of rethink how we go about doing this. So first off, the Anthropocene, what's that all about? So what I'm going to try and do in about 2 minutes' time is take you through all of modern human history, okay? So taking from something that was said on one of the flights coming over here, please fasten your seatbelts and do not sleep on the floor. So if we start off here, this side of the stage is 200,000 years ago, and the opposite side of the podium is the present day. And the oldest modern human remains that have been found so far are 198,000 years old. They were found in Ethiopia, and that's when we showed up on the stage. And we showed up on the stage as we had been sliding from a previous warm period into an ice age. So we're sliding into an ice age. We're living on the African continent. That's our home. And now we're getting to be about almost at that seat here. This is about 120,000 years ago. And something interesting happened about then. It got warm again. Okay, we came out of an ice age. We went into an interglacial period. It lasted for 15,000 years or so. And then it got cold again. And we were couch potatoes. I don't know, modern humans must be couch potatoes because we stayed home. We didn't start wandering at all. We get to about here. This is 90,000 years ago or so. And that's the first little bubble point on the left-hand side of the chart that I've got in back of me. What you're seeing here is a chart taken from an ice core, data taken from an ice core drilled in Greenland. And what you can measure in that ice core is oxygen isotopes. And the ratio of those oxygen isotopes tells you something about the temperature of the planet when the snow fell that made the ice that's in that ice core. So what you're seeing is low down on that plot is cold, up on that plot is warm. So we're about 90,000 years ago. That's when we left our African home. At least some of us did. Probably, interestingly enough, fewer than are in this room at this point. A rather small group of people left our African home. We started wandering, got to Australia somewhere around here, 60,000 years ago or so. We got to our neighborhood here in my neighborhood in Europe, maybe 30, 40,000 years ago. And in all of this time, we're hunters and gatherers. Okay, we're chasing antelopes, we're throwing sharpened sticks at them, we're gathering stuff as we go along. And it's not until we get about here or so that we started stopping being hunters and gatherers. And if we look at this chart again, that's this period right here. Compare that 10,000 year period with the previous 80,000 years. It's warmer. That's one thing that's noticeable. Another thing, it's a lot more stable. So the environmental condition that we've had for the last 10 millennia is a lot stabler and a lot warmer than the previous ice age. Right about here, about 8,000 years ago, is when we started figuring things out like agriculture. Previously, again, we had been hunters and gatherers, but now we started slowing down, stopping building cities and towns and farming and changing everything, changing our way of life. And from about here to here, that's all our societies know about our environment. The only societies that we have built up all the way back from Darius and the Achaemenid Arab Empire to the present have been built up in this relatively stable environmental condition. That's what we know as a society. It's the only condition that we were hunters and gatherers back here. So what does that mean? Let's take a look further back in time. That was the last 200,000 years from when we appeared on the scene to the present. This particular plot is now carbon dioxide. It comes from another ice core, but this one was drilled in Antarctica. And the Antarctic ice is a lot older than the ice on Greenland. So this particular ice core goes 800,000 years back in time. So that's at 8 times 10 to the 5th. That's way over on the left here. That's 800,000 years ago. The zero was about 150 years before present. And what you can see on the other axis is carbon dioxide concentration. And in that 800,000 year period, carbon dioxide concentration varied from about 160 parts per million by volume to not more than 300 parts per million by volume. So if you imagine all the molecules of air floating around in the room, a minimum was about 180 out of a million of them were carbon dioxide. A maximum in that period, 300 out of a million were carbon dioxide. That's the natural variability that the planet has exhibited in terms of atmospheric CO2 for the last 800,000 years. Where are we today? We topped a daily average of 400 parts per million by volume not too long ago. And interestingly, that little red line that's on the plot here, that's not the little red line that I drew with a little PowerPoint thingy. That's actually data. It's data taken from the Mauna Loa volcano, the observatory there. It's the longest continuous record of carbon dioxide measurements that we have in the atmosphere. And it shows just how rapidly we've gotten to where we are today, and just how far away from the natural variability that the planet's exhibited that we're at. So those are really two take-home messages from this particular image, is that we are way, way outside the range of natural variability for carbon dioxide that our planet's exhibited over the last 800,000 years, and we got there really quickly. Carbon has been talked about a lot. Obviously, there's relationships between carbon dioxide and climate change, but it's not just carbon that we've perturbed. This shows, the two plots here show a picture of the nitrogen cycle. So the upper panel comes from the year 1890. And what the arrows show are flows of nitrogen from one reservoir to another. So the N2, that's inert nitrogen gas. About 78% of what's in this room at the moment is N2, nitrogen. That gets turned into a different form of nitrogen by natural terrestrial ecosystems. So that's that little picture there that looks like a forest on the bottom, and a big arrow that goes from the atmosphere to those forest ecosystems. The little squiggly arrow that goes from N2 to NOY is lightning. Lightning makes oxides of nitrogen that eventually turn into nitric acid. So that's a pathway. That's a natural one. The other one, the NHX thingy, that's ammonia and ammonium, so it's reduced form of nitrogen, and that also has a natural cycle. Back in 1890, there was a lot of talk in the scientific world that we might be running out of fertilizer. Population was increasing. It was becoming increasingly difficult to feed that population. The British were sending ships out to islands in the Pacific and actually scraping off guano from the islands as fertilizers and bringing it back home. And there was basically a competition to come up with a better way or a different way of producing fertilizer. And that new big arrow on the bottom plot from 1990 is one single industrial process called the Haber-Bosch process. It's miraculous. From thin air, given enough energy, you can make fertilizer. And that's that big arrow going off to the right and down is industrial fertilizer production. It's doubled the amount of nitrogen that's cycling through the Earth system. We've done similar things to the amount of sulfur that's been cycling through the Earth system as well. It's double the natural state. Paul showed something similar to this in his presentation earlier today. What we've got here is a map of global agricultural land use. So the green areas are areas that we're growing crops. Could be wheat, could be maize, could be barley, could be whatever. The yellow areas, or orange, or whatever color that is, are pasture lands. So that's where we've got our cattle, sheep or cows or whatever it happens to be. And you can see that the intensity of the pixel is how intense or how much of that land area we're using or how intensively we're using it for our own purposes. And you can see that about 40% of the ice-free land surface on our planet is being used for our purposes, either as rangeland or cropland. So I've been trying to convince you that we've had a planetary impact and are having a planetary impact. And if those other plots and pictures haven't done it, for me, this one really is telling. It's an image of lights from space. It's not an artist's conception of lights from space. It's actually an image of lights from space. taken at night from a U.S. Defense System satellite, or a series of them. And for me, it's pretty interesting because really this is a plot of waste. Because if you think of what we use lights for at night, it's to illuminate the surface so that we can get around and see where we're going. And any photon that goes off into space is lost. That's waste. And that's exactly what we're seeing here. It also shows where we're wasteful. And it's a lot in the northern hemisphere. We're less wasteful in the southern hemisphere. It's not just because there's more land in the northern hemisphere. So our impact on the planet is global, but it's not even. It's not the same all over the planet. What does that mean? Rather than trying to tell you what that means or talking about sustainability issues myself, I'd like the Marx Brothers to do it for us, because you know them as comedic geniuses, but they were probably the best communicators about sustainability issues ever. So here we go.
Wood! Timber! Timber!
So Groucho's calling up timber. Harpo's bringing in some.
Timber! Timber!
And he's working pretty hard to get timber from this train. So if you kind of imagine that locomotive is our economy, and we want our economy to go faster and faster. We want growth. And it's based on resources, at least that growth to a large part is. And if it's that train, and that train is our planet, and we're using up the resources on our planet in a way that is not sustainable. And so what do you think is going to happen to the train after a while? I mean, Harpo's doesn't have an infinite amount of timber. So I really love the way that the Marx Brothers helped us out framing this concept. So, planetary boundaries. What are the implications of being in this Anthropocene, in this new epoch in which we humans are a major driving factor for really the basic cycles of the planet? Most of us scientists like to focus in on something. My own geeky scientific thing to do is I fly around on research aircraft and I try to figure out why some particles turn into cloud droplets and why some other ones don't. Okay, it sounds pretty weird, but that's what I do. Those little particles, those are probably 100th of the width of a human hair, really tiny. You tend not to see big pictures when you do things like that. But when you do back up, and when you try to take a look at the big picture, you see interesting things happening on a planetary scale. There are what appear to be quite a number of potential tipping points. That is, if you push a system a little bit, the response of that system can be very large. Despite the fact that the push is small, the response can be nonlinear, it can be quite large. There appear to be quite a lot of these potential areas. We know that when we first started figuring out agriculture 7,000 to 8,000 years ago, the Sahara wasn't a desert, it was a savanna ecosystem. It flipped from that stable ecosystem into a different stable ecosystem rather rapidly, at least more rapidly than the forcing, changes in solar intensity in it would have said. There are a bunch of other ones, like potential changes in monsoon circulation. Anybody remember that Day After Tomorrow film with everything turning to freezing and whatnot? That was based on a potential scenario of a change in the Gulf Stream circulation. So there are a number of these potential tipping points. And we started asking a question a few years back, well, are any of our human activities actually pushing on any of these potential tipping points? Can we identify what those might be? And more importantly, can we quantify a level beyond which we start getting into a risk zone in terms of that shift actually happening? And that was called, ended up being called the Planetary Boundaries analysis. And for those of us involved, it was kind of fun because usually when you come up with some new scientific idea, it stays in the geeky scientific community for a long time. And this one moved out of the geeky scientific community rather rapidly, which was a bit of a surprise. But what's it about? So what are planetary boundaries? So the planetary boundaries that I'll be talking about are all associated with some sort of very large-scale change in the way that the Earth's system work. Sometimes they're tipping points. Sometimes they're walking off the stage and falling and changing state. Other times it could be a more gradual state, like climbing up the steps to get back on the stage. But it's a large-scale change in how the systems work. There's some control variable associated with these planetary boundaries over which we humans have control. It could be the amount of fresh water we use, the amount of land we use, the amount of carbon we emit to the atmosphere. They include normative aspects of a preferred state. And this is where this particular analysis differs from a lot of other scientific analysis, is we do make a normative statement here. And our normative statement is we don't want to push the Earth system out of that stable Holocene period, because that's the only thing our societies know. That's the only kind of environmental condition that our societies know, and we don't want to move our system out of that. Further, they operate over timescales that we have that are relevant for our decision making. So if moving from one state to another would take like several millennia, who cares? That's probably slow enough that we can react to it. If it took 10 minutes, then we couldn't do much about that either. But all of these operate over decadal scale sorts of time frames. We can define what we call a safe operating space. If we know where these boundaries are, then we can flourish, and we can flourish within an environment that we might recognize, or our societies might recognize. So schematically, we've got a response variable. It could be something like the stability of the Greenland ice sheet as an example. So you've got one state where you've got a Greenland ice sheet, you've got another state where you don't have a Greenland ice sheet, and there's something in between. And for many of these variables, there's a zone of uncertainty. For some of them, the boundaries, that zone's quite wide. For others of the boundaries, it's quite narrow, like ocean acidification. Our normative judgment was that we tried to estimate the size of that zone and put the boundary on the lower end of that scale. Okay, so where do you want a guardrail if you're standing up next to the stage? Do you want it like over here somewhere, or do you want it a little bit farther back? And the safe operating space would be on the correct side of that. So when we started the analysis, we didn't know if we'd find any of these, if we'd find 615. We ended up identifying 9 and quantifying 7 of them. And those are climate change, or how much carbon dioxide we have in the atmosphere, ocean acidification. If we put carbon into the atmosphere, only about half of it stays there. And nature does us a wonderful ecosystem service by removing the other half. About 25% goes into terrestrial systems, about the other 25% ends up in the ocean. And one of the things that happen when you dissolve CO2 in water is it becomes more acidic. Your Coke is a lot more acidic than just natural water would be. Ozone depletion, stratospheric ozone depletion, how much nitrogen and phosphorus we use, how much fresh water and land we use. Biodiversity is another one of the planetary boundaries we've identified. The two we couldn't quantify. We didn't feel we had quite enough data to be able to put a number on where this boundary might be, have to do with how many particles we emit into the atmosphere, because that potentially changes weather patterns and monsoon circulations. And chemical pollution, things like hormone disruptors or even radioactive materials. So where are we in terms of these planetary boundaries? So in the pre-industrial period, now what we've done is we put a fence where we're at the boundary for each one of the dark lines around the outside of this little corral. In the pre-industrial period, we were nowhere near any of these boundaries. If we look at the 1950s and 1960s, for the data that we have available, we were also within all of the planetary boundaries at that particular point. If we look at the 1970s and 1980s, we stepped over the nitrogen planetary boundary at that point. If we look at the 90s and noughties, we were stepping over the climate change boundary, even farther over nitrogen. And if we look at the latest data, we're now over 3 of our 9 planetary boundaries: biodiversity loss, the amount of nitrogen that we use on the planet, and climate change. There is a success story here, and it's hard to see, but it's there. If you look at the ozone depletion boundary, you can see that we're actually moving away from it. It's one example where international agreements, the Montreal Protocol from the mid-1980s, actually is moving us away from one of the planetary boundaries. There are successes, or there's one anyway. So, what are some of the implications of this? What does it mean if we're across a boundary? Nature's still out there, we're still here, society's still functioning, and I just told you that we were across 3 of these boundaries. How many of us in the room own or are trying to purchase where we live, our domicile. Okay, quite a number of people. How many of you people have fire insurance? Almost the same number of hands. I didn't really notice anybody who's trying to buy a home and doesn't have fire insurance. Here in the U.S. in 2010, there were 369,500 domestic fires, and there were 130 million plus domiciles, which means you'd have to wait 350 years for your house to burn down. Okay? So we all have fire insurance, or most of us do, and we all think it's a good investment, because if my house burns down, that's nasty. That's not good. So I will pay for the very unlikely occurrence that my house burns down. And in my lifetime, the expected number of times my house is going to burn down is 0. For me, it's not going to happen. It may be that it has happened to somebody in the room, because there's enough of us. But nonetheless, from a purely crass economic point of view, fire insurance doesn't make a lot of sense. But we all have it. So what does that mean in terms of these planetary boundaries? So let's go even farther back in time than we've been so far. And this particular plot on the X scale goes back 65 million years in time. So on the one side is when the dinosaurs disappeared, and on the other side is almost the present day. I'm going to confuse everybody because the vertical axis is now on a logarithmic scale. Okay, so the first little tick mark is 100 parts per million by volume. Then it goes up to 1,000 parts per million by volume in the middle, and it goes up to 10,000 parts per million by volume on the top. So let's look way back when, 40 to 60 million years ago. And from sediment data, we can extract how much CO2 was in the atmosphere at that time. And you can see it goes from maybe about 400 parts per million by volume to a few thousand ppm. At that time, the planet was ice-free. There were no major ice sheets on the planet. Okay, the continents weren't even in the same spot as they are now, but nonetheless, the planet at that point was ice-free. Let's go to the opposite side of the plot, from 25 million years ago until roughly the present. Then we can see carbon dioxide concentrations were about 300 parts per million or lower, more like about 200 parts per million by volume. Then we had ice sheets on Antarctica. We didn't get an ice sheet on Greenland until about 3.5 million years ago, and you can see the little dip in CO2 concentrations about that time. That's when the Greenland ice sheet formed. So we've got two stable states that we know that the planet's been in. A long time ago, an ice-free stable state, carbon dioxide concentrations of above 400 parts per million by volume. The current ice planet, the cold planet, where we have ice sheets in Antarctica and Greenland, CO2 concentrations of a couple hundred parts per million by volume. The little lines on there, the horizontal lines, show projections for CO2 concentrations into the future. So we're actually at 400 parts per million, the green line now. By mid-century or so, we're going to be at 500 parts per billion by volume under a business-as-usual scenario. By 2080, we'll be at 600 ppm. And you can see we're creeping into more and more of those points where we know the planet was ice-free. So this is a risk analysis. How risky do you want to be? How risky do we want to be in terms of destabilizing the Greenland ice sheet? That's 7 meters of sea level rise if the Greenland ice sheet were to slide off into the ocean or melt. Okay, so what does that mean? What are some of the implications of being in the Anthropocene? How might that require us to change the way we operate, to transform how our societies work, as China was telling us this morning, not just incrementally, but transformationally? So let's think about feeding 9 billion people. There are 7 billion of us on the planet at the moment. Projections are we might reach 9 by certainly the end of the century or so. So how do we produce food for those 7 billion of us that are on the planet? Interestingly, we produce enough food for all 7 billion of our neighbors. We just can't get it to many of our neighbors at a price they can afford. And we have starvation because of economic reasons, not because we're not producing the food. But let's go to the production bit. So the little cartoon shows how we produce food. So on the right-hand side, I guess, there's a bunch of cows, and there's some plants, and there's an irrigation sprayer. And so we grow a lot of our food on land, either as grains, or vegetables, the plants that you see, or as cattle, the meat that we eat. We use irrigation water. Sometimes that comes from underground sources, sometimes it comes from rivers. Some agriculture is rain-fed, rain-driven. But one of the important bits of this picture is the N and the P, the nitrogen and the phosphorus that we use as fertilizer. And about 47% of the nitrogen that we apply to our fields disappears. It's either washed away and ends up in streams, or it turns into a greenhouse gas, nitrous oxide. So about half of what we apply to the field doesn't even get into the plants. And even less of what we apply to the field actually gets in the food that we consume. If you go and get a Big Mac, a couple of percent of the nitrogen that you actually bought from the vendor, or the farmer did, ends up in the food that you ingest. If you eat some pasta, maybe 10% does. Okay, so we lose much of the nitrogen. A lot of it ends up in rivers and streams and ends up in coastal areas. And I want to come back to that in a bit, but I want to hop to the marine domain first. Okay, so the little picture on the other side is a guy in a boat. So we get marine protein from two main sources. We go out and we catch it, capture fisheries, or we farm it. So let's start with the capture fisheries first. Go back to about mid-1970s or so. At that point, about half of the wild fish catch on the globe was at its maximum production potential. About 10% was overfished, which means that about 40% was underutilized, if you will, for human consumption. Fast forward to the mid-1990s, or the mid-noughties, if you will. We're still at about 50% of the global wild fish catch is at its maximum production level. But now about 30% of the global fisheries are overfished, which means we've only got 20% left that's underutilized, if you will, for human purposes. That's not a lot of wiggle room. If we look at how much fish we're actually catching, wild fish now, that has stagnated. We're not catching any more fish now than we had been in the mid-1980s, despite the fact that we're using about twice as much energy now to catch that fish than we were using in the mid-1980s. So we're fishing deeper, we're fishing farther north, farther south, we're using more energy to get that fish, and we're not catching any more fish. We are producing more fish, but we're doing that from farmed fish, from aquaculture. Anybody ever seen a fish farm? Wow, okay, cool. A number of people have. They're in coastal areas, right? So what's happening in coastal areas? Now we've got runoff coming from our agriculture production on land. It's ending up in many coastal areas. It causes algal blooms. Where I live in the Baltic, we get them every single year. Huge algal blooms. You can see them in satellites. Okay, and what happens to the algae? The algae, that nitrogen and phosphorus, that's a nutrient. They love it. It's food. So algae will grow. They're very happy. They're very short-lived. They'll die. They start settling through the water column. By the time they reach close to the ocean floor in the coastal areas, they start to dissolve. And that dissolution requires oxygen. So down at the bottom, you've got oxygen areas of dead zones, basically. There's no oxygen. If you're a fish, you can move. You can swim away from those areas. If you can't breathe, okay, I'm moving. But if you're a crab or a clam or something like that, it's kind of tough. You don't move very fast. So if we want to produce more food for 9 billion people, how do we do it? Well, if we use conventional technologies, then that would require more nitrogen fertilizer for farming on land, which means we create more problems for aquaculture, and that's where we have the wiggle room for marine protein. So I was talking about this to the UN high-level panel on global sustainability a couple of years ago, and they asked, okay, so tell us, what are some conclusions and recommendations that you might have? Well, the first conclusion is that we can't use the same, frankly, miraculous green revolution technology that allowed that to happen, that allowed us to produce enough food to feed the 7 billion of our neighbors now. We can't use that same approach to try and feed 9. It's just not going to work. But there are alternatives. We do need to invest in research and development for more efficient use of fertilizer. Remember, half of it washed away or disappeared. We can get a lot smarter about how we use fertilizer. We can get a lot smarter about how we use water to irrigate our crops. We can use novel farming techniques that are less invasive. We can promote less resource-intensive diets. Now, what does that mean? That's kind of a euphemism, but basically, again, if you're eating a Big Mac, you get 2% of that nitrogen fertilizer that we started off with. If you eat a bowl of pasta or maybe some tofu, you get a larger fraction of that. That's less resource-intensive, and I think we can probably go a long way to becoming a bit less red meatish in the future. Concentrate on optimizing food systems. When we think about food production, we think about just that, production, but that's only one small part of the food system. There's a tremendous, embarrassing amount of food that's lost just because we throw it away. And we throw it away because we don't store it properly, or it's lost when we transport it from point A to point B. We need to be able to change the way we market, dispose, store of our foodstuffs. And when I was giving the talk to this bunch of politicians, they were all kind of nodding on these first series of recommendations because they all kind of made sense. And yeah, you know, investing in research and development on agricultural systems, that's a good thing to do. Got to this last one about re-examining agricultural subsidies, and everybody had to check their BlackBerry. It was kind of amazing because this is one of the big hot potatoes for any politician, certainly in Europe. The agricultural subsidies here in North America, in the US, and in Europe are huge, and they're moving us in the wrong direction. And if we need to really get to grips with this problem, we need to transform that aspect of how we incentivize our actions and the things that we do. So to touch on where we've been, we've talked a bit about the Anthropocene, we've talked a bit about transformations towards sustainability, feeding 9 billion people, but I want to leave you with a series of images. Because we tend to think that what we have now, it's always been this way. And I get the question a lot, well, you're talking about transformative change, isn't it too difficult? Well, okay, let's think about that. This is a picture from Rochester, New York, a little over 100 years ago. And if we want to transform our societies to a more sustainable pathway, it's not rocket science. We need to look at our transportation system, our energy system, our agricultural system. If we look at this image, we can see horses and carriages. We can see electrically powered streetcars. You can see motor vehicles at that point. You might even, if you're careful, way up at the top of the image, see something that might be an electric-powered car. It wasn't clear at this time, 100 years ago, what the dominant form of transport would be. The internal combustion engine automobile was not the obvious choice at this point. We had other choices. We happened to make one. I want to show this image because this hits, for me, close to home. This image was also taken a little over 100 years ago. The guy there is my grandfather, Frank Noone. So Grandpa Frank, this is everybody, that's Grandpa Frank. He and his companions were looking for gold in Alaska. They didn't find any, unfortunately. But they were looking for gold. The really important picture or bit of this image wasn't Frank and Company, it was Frank and Company's method of transport. Once again, this is 2 generations ago. This is my grandfather. Major form of transportation was a horse. So in that time, in those 2 generations between my grandfather Frank and myself, we have in fact transformed our transportation sector. We have in fact transformed our energy sector. We have in fact transformed our agricultural sector. It's not impossible. We've done it. We need to do it again, and we don't have that much more time than those 2 generations to do it. We've got to be a bit more smart. So this is the penultimate image. That's not the Earth. That's Saturn. And I don't know if you can see it, but there's, towards sort of the center of the image, is a little tiny dot, bright dot, that you can see through the rings of Saturn. Okay? Some people are nodding, yeah, I can see that. That's us. That's our planet. That's the only planet we've got. There is no interplanetary insurance company that can bail us out if we screw things up. It's up to us to figure out how to make that work for all of our neighbors in a way that's equitable for all of our neighbors. And that's really what the Anthropocene is about. So with that, thank you very much. Once again, it's a real pleasure to be here and to be able to interact with all of you on this